Imagine unlocking the hidden secrets of matter, not by breaking it apart, but by simply shining a light on it. This isn't science fiction, it's the profound reality of spectroscopy. It's the science of how light and matter interact, revealing the composition, structure, and dynamics of everything around us. At its core, spectroscopy is about energy exchange. When electromagnetic radiation, from radio waves to gamma rays, encounters a substance, it can be absorbed, emitted, or scattered. Each of these interactions provides a unique fingerprint of the material. This fingerprint is a spectrum, a plot showing the intensity of light as a function of wavelength or frequency. Analyzing these patterns allows us to identify elements, characterize molecules, and even understand processes occurring at the atomic level. It's like listening to the unique musical note each atom or molecule plays. Every atom and molecule possesses distinct energy levels. When light energy matches the difference between two of these levels, an interaction occurs. This quantum mechanical dance is the basis for all spectroscopic techniques. The type of interaction depends on the energy of the light and the specific properties of the sample. From electronic transitions to molecular vibrations and nuclear spins, each phenomenon has its own spectroscopic window. Understanding these fundamental principles is key to interpreting the data. The electromagnetic spectrum is vast, and different regions probe different aspects of matter. Ultraviolet and visible light interact with electron transitions, while infrared light excites molecular vibrations. Radio waves, on the other hand, can manipulate nuclear spins. Each region of the spectrum offers a unique lens through which to view the world. By selecting the appropriate wavelength, scientists can target specific molecular or atomic features. This versatility makes spectroscopy an indispensable tool across countless disciplines. One of the most common forms is absorption spectroscopy. Here, a sample absorbs specific wavelengths of light, and the remaining light is measured. The wavelengths absorbed correspond to the energy required to promote electrons to higher energy states or to induce molecular vibrations. UV-visible spectroscopy, for instance, measures the absorption of light in the ultraviolet and visible regions. It's widely used for quantitative analysis, determining concentrations, and identifying chromophores in solutions. The Beer-Lambert law is fundamental to its application. In contrast, emission spectroscopy measures the light emitted by a sample after it has been excited. This excitation can come from various sources, such as heat, electrical discharge, or even other light sources. The emitted light reveals the energy levels of the excited species. Atomic emission spectroscopy, like inductively coupled plasma atomic emission spectroscopy, is crucial for elemental analysis. Fluorescence spectroscopy, where molecules absorb light at one wavelength and emit at a longer one, is vital in biochemistry and medical diagnostics. It offers high sensitivity for detecting specific compounds. Infrared, or IR, spectroscopy focuses on molecular vibrations. Molecules absorb IR radiation at specific frequencies that match their natural vibrational modes. This creates a unique fingerprint region in the spectrum, allowing for the identification of functional groups and molecular structure. Different bonds and functional groups vibrate at characteristic frequencies, providing detailed structural information. IR spectroscopy is invaluable for quality control, polymer analysis, and identifying unknown organic compounds. It's a powerful tool for understanding molecular architecture. Nuclear magnetic resonance, or NMR spectroscopy, is arguably one of the most powerful techniques for determining molecular structure. It exploits the magnetic properties of certain atomic nuclei, like hydrogen or carbon-13, when placed in a strong magnetic field. Radio frequency pulses perturb these nuclei, and their relaxation back to equilibrium is measured. The chemical environment of each nucleus influences its magnetic properties, leading to distinct signals in the NMR spectrum. This allows chemists to deduce the connectivity of atoms, the spatial arrangement of groups, and even dynamic processes within molecules. NMR is indispensable in organic chemistry, drug discovery, and material science. Raman spectroscopy is another vibrational technique, but it relies on inelastic scattering of light. When monochromatic light interacts with a molecule, most light is scattered elastically, Rayleigh scattering. However, a small fraction is scattered inelastically, gaining or losing energy to molecular vibrations. This energy shift, known as the Raman shift, provides information about the vibrational modes of the molecule. Raman is complementary to IR spectroscopy, often providing information about non-polar bonds that are IR inactive. It's excellent for aqueous samples, surface analysis, and identifying minerals. The applications of spectroscopy are incredibly diverse. In medicine, it's used for disease diagnosis, drug monitoring, and surgical guidance. Environmental scientists use it to detect pollutants in air and water. Astronomers analyze starlight to determine the composition of distant galaxies. Forensic scientists employ spectroscopy to identify unknown substances at crime scenes. Food scientists use it for quality control and authenticity testing. From developing new materials to ensuring pharmaceutical purity, spectroscopy is an omnipresent analytical powerhouse. It truly bridges the gap between the microscopic and macroscopic worlds. Spectroscopy continues to evolve rapidly, with advancements in miniaturization, sensitivity, and data analysis. Hyperspectral imaging, for example, combines spectroscopy with imaging to create detailed chemical maps of surfaces. Quantum technologies are pushing the boundaries of what can be measured. As our understanding of light-matter interactions deepens, so too will the capabilities of spectroscopy. It remains a cornerstone of scientific inquiry, constantly revealing new insights into the fundamental nature of matter. The future of discovery is undeniably illuminated by spectroscopy,